Hello everyone. So in today's video we're going to talk about gliding, which is a special case of descent basically. And the way it's special is because the term refers to basically unpowered flight. So it's basically an unpowered descent. And we finished off in the previous video talking about the sort of normal descent, and we started from writing up the forces which act on the aircraft during a normal descent. And the major difference in the case of the gliding from the previous case is that the thrust is going to be a zero vector. So the thrust is basically zero. This can happen in multitude of ways. One of the more normal everyday conditions is when an aircraft isn't equipped with a power plant altogether, right? So for example, gliders are of course the best example for gliding, but so gliders which have no power plant. Well, in most cases, of course, there are some aircraft, there are some gliders which have either a towing motor or, a sort of hidden power plant in the fuselage, which they can basically deploy and start during the flight to get back home. But we're not talking about those in general. So we're talking about general gliders, which have very nice aerodynamic shape. You can look them up. Some of you have already flown gliders, so you know this sort of experience, right? So these aircraft have, I would say, aerodynamically speaking, like a similar concept as the powered airplanes. They're just more streamlined in a way, and of course have much larger aspect ratios and much smaller aspect ratios and larger wingspans compared to the powered airplanes. Right, so these are the gliders, one example. But here's why we have to talk about this, is because if you have either a single engine or twin engine, an aircraft with 3 engines, 4 engines, so a multi-engine powered airplane which has an all-engine failure. So all-engine failure of powered airplane. One example would be a famous one, right? So the landing on the Hudson, where an Airbus 320 fairly quickly, shortly after takeoff, pretty much turned into a glider that they ride, because it still had the 2 engines intact, but they were so damaged from the collision with the birds that they didn't produce like almost any thrust. So in this regard, the two scenarios are the same, from flight mechanics point of view and from aerodynamics point of view. In that case, we will see that the same thing matters for the glider as much as for the powered airplane, which has lost all of its engines. So we're not gonna talk differently about them. And of course, so again, in this case, the engine failed, so there's no thrust being generated. And the same goes for any light airplane construction. So for example, if the Piper has an engine failure for some reason, in that case, the same applies, right? So the aircraft is going to start to come out of the sky the same way the Airbus would or the glider does, right? Because the engine has stopped, it's no longer generating any thrust. So aerodynamically speaking, these three scenarios are essentially the same, which leads to a bit less complex conversation, and a more pure one from aerodynamic point of view, because we don't have to again deal with the anomalies of the power plant, and we don't have to deal with the thrust being generated. So let's start with looking at the examining the forces during light. Right, so it's going to be very, very similar to the normal descent, with the exception of the thrust force being present. So of course we have we're going to have the local horizontal, and we're going to have a flight path along which the center of gravity of the aircraft travels along, and between them we're going to have a flight path angle, and along this flight path we're going to have, let's say in this example, a glider. Right, so here we have a good old glider. It's very streamlined, very modern. Here you have the cabin and everything nice, and of course the horizontal stabilizer. Okay, so of course here we have like a local vertical, as we call it, the ZE axis, so the vertical axis in the Earth coordinate system. And here we have the local horizontal, which we could say is the longitudinal axis in the Earth's coordinate system. Okay, so of course, if that's true, we're going to have gravitational acceleration acting in the vertical direction, in the vertical axis of the Earth. And since we're going to have the undisturbed airflow, relative or undisturbed airflow coming from the longitudinal direction of the aircraft, right? So Vy and Vz. So therefore this is going to be minus V 0, 0, because we forgot to mention that of course this one is going to be parallel with the aircraft's longitudinal axis, and perpendicular to that we're going to have the vertical axis of the aircraft, right? And the two are perpendicular to each other, of course. Okay, so let's gather the forces acting on the aircraft. So we're going to have the lift, which is going to be perpendicular to the relative airflow. We're going to have the drag, which is parallel with the relative airflow, so right here. And of course we're going to have the weight of the airplane, because of course the aircraft is going to have a mass, so the mass times the gravitational acceleration of course gives us the weight of the airplane. So it's going to be somewhere right here. So this is the weight of the airplane. Okay, so if we want to collect or summarize the forces in the axis of the aircraft, we're going to have to break down the weight into components of the vertical and longitudinal axis. So there's no surprise in that. We've done that quite a number of times, so you guys already know that this is going to be the equal to the flight path angle. Basically from here we're going to pull perpendicular to the vertical axis, and we're going to break down the weight into two components basically. So one is the Wz, which is going to be equal to the cosine of gamma times the weight, and we're going to have the component parallel with the longitudinal axis, so like this. It's going to be equal to the sine of gamma times the weight. Okay, so now if we want to gather or collect the forces, now we can do so. And again, since this situation is going to be a steady glide, a steady descent, we can presume that the acceleration is going to be a zero vector, again, which means that all three components around the aircraft's coordinate system are going to be zero, right? And so we also know that the acceleration is going to be in the three coordinate axes is going to be the sum of the forces in the x direction over with the mass, the sum of the forces in the y direction over with the mass, and the sum of the forces in the z direction over with the mass, right? Because I think it's easy to see why. Let me elaborate a little bit on this one. So this one is true essentially because if we want to break down the acceleration vector in the aircraft's coordinate system, it's going to be given to us by an acceleration parallel with the longitudinal axis, an acceleration parallel with the y-axis, and an acceleration parallel with the z-axis. And we know the basic formula, right? That the acceleration is going to be the sum of the forces over with the mass. So we can basically substitute this formula for every single component, and this is how we get here, basically. Right, this is how we get here. Right, and so therefore we can see that we have to divide with the mass in every single component of the vector, so we can transition that 1 over mass, and what's that gonna leave us with is a vector with the sum of the forces, right? Sum of the forces in the x direction, sum of the forces in the y direction, and sum of the forces in the z direction, which basically equals the form like sum of the forces vector over with the mass, which is a scalar, basically, right? So it's the same exact form. But what we need to sort of understand from this is that every single component and this whole vector needs to be a zero, right? So how can it be zero? Since the mass in the denominator cannot be a zero, right? Because the aircraft has to have a mass in order for us to have this whole discussion. So this whole expression is definitely not equal zero. And well, we also know that it's definitely going to be a positive number as well, but we don't need to go into that kind of detail. So it's definitely not zero. So the only way this expression can be equal to zero is that if this matrix, this vector right here, is a zero vector, right? So therefore, it would mean that the 1 over mass has to be multiplied with a 0, 0, 0 vector. So therefore, from all of this, we understand that the sum of the forces in the x direction, the sum of the forces in the y direction, the sum of the forces in the z direction, or actually like the vector, the matrix containing these values, has to be 0 in every single case. Right, and this is where we'll begin from. Right, so let's start gathering the sum of the forces in the x direction. So the sum of the forces in the longitudinal x direction are going to be basically in the positive direction, the sinus gamma times the w times the weight. And in the negative direction, we have the drag, right? So in the negative direction, we have the drag. And we know from this equation, which we previously expressed, that this whole expression has to equal 0. So therefore, we can say that the sine of gamma times the weight is equal to the drag. So therefore, we can basically express the sine of gamma from this equation. And what we get is that the sine of gamma is equal to the drag over with the weight. So this is the result that we get here. Okay. From the second one, so if we summarize the forces in the y direction, we we presume that there is no force during a level glide. So with the bank angle being 0, and flown in a coordinated manner, we presume that the sum of the forces in the y direction are essentially zero, right? So no forces acting there. Okay, so let's collect the forces acting in the z direction. So we can see that in the positive direction we have the cosine gamma times the weight. So actually this can be quite confusing, so let's delete that. Okay, so we have the cosine gamma times the weight, and in the negative vertical direction we have the lift, which is minus the lift, and this whole expression, we know that from this one, is going to be equal to 0. So therefore we know that the cosine gamma times the weight is going to equal the lift, and if we express the cosine gamma, we get at the end that it's going to be equal lift over weight, right? And these are the two sort of expressions that we get out of this whole discussion of writing out the forces. Okay, but here we're going to do a little bit of trickery, right? Because here we cannot really establish too many effects of how the drag, how the lift, and how the weight essentially affect the flight path angle, right? Because, for example, let's look at the effect of mass on the sinus gamma, right? Or on the flight path angle, basically. Well, of course, it's gonna reduce from a point, because we can see that in the denominator the weight is going to increase. However, the drag is also going to increase, right? Because we have just a very quick sketch: true airspeed, we have the drag, we have the drag for the light airplane, and if we add mass, the whole diagram is going to move up and to the right, and we will see that the drag is also going to increase. So, and so what's the final combination here, right? So how does mass, for example, influence the flight path angle? Okay, so to understand that a little bit and to understand the influencing factors a bit better, we need to do a little bit of trickery. So we know by definition that the tangent of an angle, let's say tangent gamma, is going to be equal to the sine of the same angle over the cosine. So now let's substitute the values we got from the sinus gamma right here and the values we got from the cosine gamma right there, right? So what we're going to get is that the sine of gamma equals to the drag over weight, and the cosine gamma is the lift over weight. And so if we want to divide by it, we can multiply by the inverse of the fraction, right? So we're gonna multiply it by weight over lift. And so what we can see is that we can simplify with the weight, and what we're left with is the drag over lift, right? So we can further express this formula and say that the drag is essentially going to be equal to the drag coefficient times the half of the density times the true airspeed, or we could simply say at this point, because it's depending on what kind of velocity we're talking about and what kind of density, let's just say velocity squared times the surface area, right? And we can express the lift as being the lift coefficient times half of the density times velocity squared and times the surface area. Okay, now as you can see, we can make some simplifications. So the velocity is present in both terms, the surface area and the half of the density is as well. So what we're left with at the very end is a drag coefficient over the lift coefficient. And so let's express it in a final form. So what we received in this whole discussion is that the tangent of the gamma of the flight path angle is going to be a function of the drag coefficient over the lift coefficient, right? And this one is very interesting. The reason why it's interesting is because what it's telling us is that the flight path angle, this one, is only a function of the ratio between the drag coefficient and the lift coefficient, which are both basically aerodynamic properties of the airframe of the aircraft. It's very interesting because the weight is not present. So the mass of the aircraft, as we can see, will not influence the flight path angle. And so therefore, what we're looking to do in a glide, usually, we can optimize for two things. We can optimize for the range, and we can optimize for endurance. And let's talk about range, optimizing for range a little bit. Right, so if you want to basically optimize for the range, you want to get the best range that you can get. And again, like, what is the tangent of this flight path? So the tangent gamma of this flight path is going to be, if we have right here the local horizontal, so this is basically the ground, right? So here we have the ground, and we're going to start from like a given altitude, a given pressure altitude, a given Z, and we're gonna, this is gonna be our flight path right here, let's say. This is gamma, and this is going to be the distance covered on the ground. I could actually use a different color to make it visible. And actually, let's use vectors for this one as well. So we start from right here, and we move down here. Right. So the glider starts from this point right here. Whether that is a glider or a powered aircraft which has lost its engines, it doesn't really matter from this point of view. Right. And so we start from a given point, and the tangent of this gamma, as we can see, is going to be equal to the, let's say this is delta Z, like the vertical distance that we cover during the glide, so the delta Z, over with the, let's say in this case it's going to be relative to the ground, so let's say x, g, and d, so the longitudinal distance covered relative to the ground. Essentially, we always talk about a distance covered in the air, and this would be still air condition, but we'll talk about the effect of the wind a bit later, right? So this would be the tangent of the flight path angle, relative to the ground, of course. And what this tells us essentially is that how much altitude you're going to lose for a unit amount of ground that you cover. Or in other words, from losing the same amount of distance or vertical distance, so losing a given amount of altitude, how far will you get? What is the horizontal distance that you can cover relative to the ground? And I think it goes without saying that it would mean in that case that the best range would occur exactly where this flight path angle is shallowest, right? Because what happens if from the same delta Z, from the same altitude, I would fly with a shallower flight path angle? Let's say this is gamma, gamma B, right? And so now I've covered this much ground, right? So I've covered this much ground, X, G, and D, B, right? So what we can see is that, the shallower the flight path angle, the better the range, right? So therefore, the the best range is going to occur when the flight path angle is minimum, right? So that's where the best range from a given altitude is going to occur. So best range. So what we're looking for is basically to minimize this angle. We're gonna looking for the minimum of the tangent gamma. So where that occurs, if we remember from the previous discussion, is that the tangent of the flight path angle was the drag coefficient over the lift coefficient. So therefore, I'll continue this a little bit lower. So where the CD CL is min, the CL over CD, so the lift coefficient over the drag coefficient, has to be a maximum, right? So I think it makes sense to say that we're looking for the best lift coefficient to drag coefficient ratio. And for this one, we can rely back on the polar curve of the aeroplane. Again, let's just quickly sketch up a general polar curve so that we can better visualize it. So of course here we have the lift coefficient and the drag coefficient, and let's say here we have a very general looking, well, a very general looking like polar curve like this, right? So essentially what you're looking for is the CL CD to be maximum. So for any given point, so for this point, for example, you know, if I connect the origin of the coordinate system with this point, this one would be my CD ratio, right? Because if I read off this point horizontally, it's going to be equal to my drag coefficient, this one, right? So I think it makes sense. It's the same distance as from here to here. So therefore I can like project it up to this point. And this value right over here, I think it makes sense, would be my lift coefficient. So what you're looking to maximize is your, or minimize therefore, is your CDCL, again, this one, right? So you're looking to minimize, and again, the tangent gamma was the CDCL. So can you find the angle which has on the opposing side the drag coefficient, and on the adjacent side the lift coefficient? I'll give you guys a little bit of time right in this triangle. So of course it's going to be this angle right here, right? Because essentially the tangent, and here we have a right angle, so the tangent for this gamma angle is essentially going to be the CD over the opposing side over the adjacent side, right? So this drag coefficient over the lift coefficient. So we're looking for the point where this gamma angle would be minimum, right? Because where the tangent gamma is minimum, where the gamma is a minimum. So of course that's going to occur at a very convenient place, at basically exactly the tangent of the curve, right? So here you're going to have a given CD, the drag coefficient, and here you're going to have the corresponding CL to this point. Actually, we can call this like optimum, CL opt, and here we're going to have the gamma min, basically. Like this is like the shallowest angle that you can achieve. Because if you think about it, at any other point, starting from here, you know, here it's fairly big. It's basically 90 degrees, right? And it starts to become shallower, 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 until we get to the tangent. And after the tangent, of course, as you can see, it's going to continue to increase yet again as we go through the entire curve, and the same thing backwards. So it's going to be the lowest when we get to the tangent. So I think that makes complete sense. So by this time you already know where the at what speed this this best CL Cmax or CL/CD ratio occurs, because here at this point the drag coefficient over the lift coefficient is minimum, so therefore the lift coefficient over drag coefficient is maximum. So therefore you already know that this point, or should know that this point occurs at VMD, right? So exactly if we maintain this VMD, we're going to get the shallowest flight path angle, and we're going to glide the furthest. On the other hand, if we're maintaining another speed, or a speed other than the VMD, this angle is going to be larger, right? So what this means, if the angle is essentially larger than this one, the shallowest one, in that case your flight path is going to be steeper, and so therefore your range is going to be smaller as well. So this is, I think, a very, very important lesson for us, especially when we're going to be training for the forced landings without an engine, is that you guys can see how important it is to maintain the correct speed, right? Because if you maintain any other speed than the optimum gliding speed, or the best glide speed, as it is usually denoted in the pilot operating handbook of any aircraft, you're going to reach the ground at a smaller range. And if you think about it, at any scenario, whether you're gliding or whether you're flying a powered aircraft, your range is the number of options that you have from any specific point of view, right? And to give you guys an example, you have an engine failure with a Piper, right? You have your little Piper, and the engine stopped operating. And let's say that you have a whole bunch of fields ahead of you. You have a whole bunch of fields ahead of you. But again, you see one which is, nice and really big, and would really, looks like a safe spot. It doesn't really have too many obstacles. And the ones which are closer to you, essentially have maybe, power lines going through them, or, have rough texture. So, and they're smaller in size, so they don't really look that good. So you're looking to get to this field. And what the range means essentially is that from the center position where you currently are, you're gonna draw, well, almost, if we don't take into consideration the altitude loss because of a turn, because essentially, when you're turning, as we saw in the beginning of the course, you'll be losing more altitude during a turn, because to generate that force which keeps you into the turn has to be sort of compensated for by the lift which you generate. So essentially you're going to be descending more. But what it means, what the range means, is that you have a given radius. You have a given radius from your current position where you can still glide to, and this is your X, G, and D, right? If we take this whole two-dimensional image, if we take this whole two-dimensional image and sort of rotate it around rotate it around the vertical axis, basically, you're going to get this picture from a top-down view, right? And so what this leads to is essentially the number of options which you have. And so let's say that if you maintain your best glide speed, you're going to have the most options. However, if you fly faster, for example, if you fly faster because you think that that's going to be safer, you're actually, what you're doing is you're reducing this distance to where you can glide, right? And so xg fast, So you're reducing basically the number of options that you have because you're sacrificing a lot of the range to generate a larger speed. So basically you're converting your potential energy to kinetic energy at a much faster rate than would be optimum. And so therefore you dissipated that energy to convert it to kinetic energy, which you're not essentially getting back, because you can zoom out from a given position and you can use that extra kinetic energy to maybe even maintain altitude or something like that. But of course there's always a loss of energy during a glide or during any mechanical transformation. So you're not going to get back the same potential energy which you transferred into the kinetic energy, much less, right? Because there's energy loss twice. So what we mean to say by this whole discussion is that essentially if you're not gliding at the best glide speed, but if you're gliding at a faster rate, what this means is that essentially you're going to, because again, where are the faster speeds on this diagram? So this is the optimum. So faster speeds are at this range, right? So if you increase your speed, you're going to get a larger flight path angle. Larger flight path angle means a smaller range, right? So larger flight path angle means smaller range. And essentially this is what it does. You're losing probably very good options, or more than the more number of options that you have, and you're also losing like time in the air. So what happens if you are a bit more pessimistic and you think that you're gonna get faster if you fly slower, right? So from this point, if you start flying slower, it means that you're essentially moving along this side of the curve. Well, as you can see, again, because we're outside of the optimum, your flight path angle is going to increase again. So if your flight path angle increases, compared to the optimum, that means your flight path angle is going to increase. So your range is going to decrease. So again, maybe by the same amount, it depends on, what speed you're flying at. But again, your range is also going to reduce if you're flying too slow, xg slow. So essentially, you're always losing a number of options when you're flying at a different speed than what would be optimum. So this is why even during an emergency drill or an actual emergency, or when you're gliding, for example, when you're gliding, it's a bit different because there's a whole lot of different strategies you might want to use. So we're not going to go into detail into that one. But essentially, especially with the powered airplane, which had lost its engine, basically you always want to fly with the best glide speed, because you're always looking to optimize range, because range is giving you options. And that's what you want the most. You want to have more options to choose your landing place, and maybe even, if the situation occurs, maybe you can even reach the runway, right? So maybe the runway is still within reach if you fly with the correct speed, but if you fly at other than the optimum or other than the best glide speed, you're not going to make the field, you're not going to make the runway, you're instead going to have to make a forced landing, and maybe much worse, you'll be forced to make the landing in much worse conditions than you originally would have anticipated, and this is what's most critical, than what the airplane's aerodynamic conditions would have enabled, because the aerodynamic properties of the aircraft might have enabled you to get back to the runway, but an incorrect flying technique made you lose a bunch of options, and now you're left with only the bad options, and you're not reaching the runway because of basically bad flying, because that's a bad flying. But we're not, of course, overemphasizing the bad example, so you're looking to be doing the good thing. So the important thing to remember here is to always, in case of an emergency, establish as soon as possible the V, and this is how you can fly it in the pilot operating handbooks, is the VBG. VBG is the best glide speed. And if it's not available, then you always know that the best glide speed is going to be the VMD. And again, we're not going to examine differently like the jet propulsion, the propeller driven, and maybe the glider, because as we said in the very beginning, all these cases are, from this discussion, are essentially the same. Right. Okay, so this is what happens when we're flying for range. Sometimes you might want to be flying for endurance, but about that we will talk after having discussed the effects which affect the range of the aircraft, essentially. So what conditions do you think affect the range? We said that the mass doesn't, right? Because in this tangent gamma, we only have the drag to lift ratio, right? Or the inverse of the lift to drag ratio, essentially. So the mass does not affect the range of the aircraft. Well, essentially, it does affect something. So again, it doesn't affect the flight path angle, but let's draw up the or plot the drag in function of the true airspeed. So what we're going to see here is that we have the drag for the light airplane, right? And we said that the best endurance would occur in the VMD. And that's also visible. I wanted to mention that as well. It's another approach, as we said initially up here, is that the sine of the gamma, or sinus of gamma, is the drag over with the weight, right? So drag over with the weight. So for a given mass, of course, the velocity where you can maintain the smallest sine of gamma is, of course, where you would minimize the drag. So therefore, VMD, right? So it's also another approach. So you want to minimize the drag, so therefore that happens at VMD. But of course, it doesn't affect doesn't explain how mass affects the flight path angle. Okay, so here you would have the D min, or the D light min, let's say DL min. Okay, so what happens when you increase the mass of the aircraft? We already stated that the gamma would be unchanged. However, the whole curve moves up and to the right. And so what happens is that the curve essentially looks like this one. So the drag heavy, right? So essentially, the drag heavy mean increased because of the increase in mass, and also the VMD heavy is larger than the VMD light. So therefore, the flight path angle hasn't changed, but we need to maintain a higher speed to be able to maintain the same flight path angle, right? I think, and I hope that makes sense to everybody. So essentially, the effect of mass on the glide, of mass on the glide is that the flight path angle is unaffected. So it's going to be essentially the same, right? So the flight path angle is the same, so therefore range is unaffected. Okay. However, you have to maintain, so VMD is going to become higher. So you're going to have to maintain a higher speed to maintain the same flight path angle. And that is the sort of picture that we need to get from the glide and the effect of mass on the flight path angle.